Go over the answers to your fusion pages 240 to 243. What happens during a nuclear reaction? Our essential question is, how do nuclear reactions differ from chemical reactions? By the end of the lesson, you should be able to distinguish nuclear reactions from chemical reactions and compare the types of nuclear reactions. For number 1, we had to look at this atom and use the model to help us say what the nucleus contains. Did you remember protons and neutrons? Protons are the positively charged particles in the nucleus. Neutrons don't have any charge. List 3 things that you think of when you hear the word radioactivity. A lot of people have negative connotations when they think of radioactivity. They think it's dangerous. They think of radioactive waste and nuclear radiation after an explosion. Other things you might think of are cancer or damaging rays. By the end of this unit, though, I hope that you see some positive ways that we use radioactivity. Number 3, many English words have their roots in other languages, and we have to use these Latin words to figure out the meaning of the words fission and fusion, 2 of our vocabulary words. For fission, let's look at the word physis, which means to split. The nuclei of large atoms undergo fission in nuclear power plants. So fission might mean when the nuclei of large atoms split. How about fusion? The example sentences in stars, small atoms undergo fusion to form larger atoms. And physis means to melt. So fusion might mean when small atoms join together. Our vocabulary words are listed in number 4, nuclear reaction, nuclear fission, isotope, nuclear fusion, and radioactive decay. You can use any method you want to keep track of your vocabulary this unit. Maybe do another set of Google Slides, or you could do some Quizlet slides for your vocabulary, or just write them down on paper. Here's a picture that shows the photographic paper that Henry Becquerel used as evidence for nuclear radiation. He didn't know what he was looking at yet, but he could tell energy was coming from this rock that had been sitting on a package of photographic paper. The energy from the rock caused the photographic paper to develop these spots. A nuclear reaction is what he was observing, but he didn't know it at the time. Nuclear reaction is a change that affects the nucleus of an atom. Let's look at the differences between nuclear reaction and chemical reaction. In a nuclear reaction, some of the mass changes to energy. But in a chemical reaction, mass always stays the same. We learned about the law of conservation of mass, which says that mass always stays the same. Einstein was the one who came up with the equation that demonstrates how mass is converted to energy. E equals mc squared. E stands for energy, m stands for mass, and c is the speed of light. A little bit of mass changes into a lot of energy during a chemical reaction. In a nuclear reaction, the nuclei of the atoms change. But in a chemical reaction, the nuclei of the atoms do not change. That's because in a nuclear reaction, the reaction is taking place inside the nucleus. But in a chemical reaction, the reaction takes place on the outside of the nucleus with the electrons. In a nuclear reaction, remember that the identity of atoms can change. If the nucleus changes, you might end up with a different atomic number, and so a different type of element. The identity of atoms do not change, however, in a chemical reaction. The atoms that you start with in the reactants are the same atoms that you end up with in the products. They just form different molecules together. Let's do number 5. What happens to the mass of atoms during a nuclear reaction? Some of the mass changes to energy that is released during the nuclear reaction. And on page 243, number 6, you had to underline what happens during a nuclear reaction that does not happen during a chemical reaction. Check your notebook and make sure that you underlined the right parts. During nuclear changes, if the number of protons changes, then the identity of the atom changes. That is because the atomic number is different. And this happens when carbon-14 is formed. In the upper atmosphere, nitrogen can be bombarded with neutrons, and the neutron can cause a nuclear reaction to happen and form carbon-14 plus 1 proton. So the neutron goes in and bumps out a proton, which now makes the atomic number 6 instead of 7. If only the number of neutrons changes, then the identity of the atom stays the same, but it's a different isotope of the element. That means it'll have a different mass than the original element before the reaction. You can open the slides at the end and click Learn More to find out more about this reaction. Remember that an isotope is an atom with the same number of protons but different numbers of neutrons. This picture shows lithium-6 isotope that has 3 protons and 3 neutrons and a mass number of 6. Because of the mass number of 6, that's why we call it lithium-6. This is the isotope lithium-7. It still has 3 protons because that's its atomic number, but lithium-7 has an additional neutron, giving it a mass number of 7. Number 7 says, draw an isotope of beryllium-9 that has 2 more particles in the nucleus than the beryllium-7 isotope below. Label the protons and neutrons in your model. So this is beryllium-7. It has a mass number of 7. It has 4 protons because beryllium always has 4 protons. That's its atomic number. It has 3 neutrons and 4 electrons. The protons and neutrons added together give us the mass number 7. You name an isotope of an element by placing the mass number next to the right of the element name. We know that beryllium-7 has 4 protons. Its atomic number is 4, so it must have 3 neutrons to make a mass number of 7. Beryllium-9 would still have 4 protons, but it's going to have 5 neutrons. This is what we have to draw, beryllium-9. So I have put a diagram together with 4 electrons, 4 protons, because the atomic number of beryllium is 4, and 5 neutrons, so that together they will add up to 9 as the mass number. And we'll put them in like this. Yours should be labeled protons, neutrons, and electrons.